Together, we looked at hybridization of orbitals within the same atom. Okay, so valence bonds theory talks about hybridization as well. Remember that hybridization happens within the same atom. So carbon atom and those orbitals are mixing together. So if this is a carbon atom, let me just redraw that. Here's a carbon atom. A carbon atom has an s orbital and some p orbitals. When you mix those together, then the carbon atom will have an sp hybridized. So you're using the same atom and mixing the orbitals inside the same atom. For bonding, we are using different atoms. Okay, so we're looking at a hydrogen atom and its s orbital, and another hydrogen atom and its s orbital. The overlap is when this electron from that hydrogen and this electron, that hydrogen share a space between the two H's. Okay, that is called, that's a bonding theory called valence bonding, because we're using the valence bond theory because we're using the valence electrons. So let's look at two different types of bonds. There's the sigma and there's the pi. The sigma bond happens when there's a head-to-head overlap. I'm showing a head-to-head collision between two cars. For example, here's a hydrogen, here's a hydrogen. There, it's a head-to-head overlap between this electron orbitals and this electron's orbital, and then they bond. If you want to bond between HCl, then you use a head-to-head collision with the electron from the H and then the electron from the Cl, the seventh electron in the 3p sublevel. Another sigma bond. Okay, here's another sigma bond in Cl. Electron here, electron here. Okay, sigma bonds are characterized by a head-to-head overlap. It is a cylindrical symmetry of electron density about the internuclear axis. That means in between the two. That's the axis between them. Okay, now pi bonds. Pi bonds are a little bit different. They are a side-to-side overlap. Okay, so if you can see here, it's not a head-to-head collision or overlap like this. That would be a sigma. That's a sigma bond. This is a pi bond. Okay, and this happens because in the p sublevel there are three orbitals, one on the z-axis, this is pz. Oops. This is the px, and this is on the y-axis. So if you have a px of one atom and a px of another atom, you'll do a sigma. If you have a pz and a pz, you'll do a pi. Okay. Single bonds are always sigma bonds. Okay, so they overlap head-to-head first. Okay, so over here, that is a sigma bond. Head-to-head overlap. Okay. In a multiple bond, one of the bonds is a sigma, so this is a sigma bond, and the other bond is a pi bond. So you can imagine, here's the C, here's the carbon atom on the p orbital on the x-axis. There's another carbon, a carbon here and a carbon there. When they combine, they will overlap these, right? So that's a sigma bond. Now, when you have a double bond, then the y or the py might overlap with each other and bond. So there's a bond there and a bond there. Okay, that would be a double bond. If you had a triple bond between an N and an N, this is what it looks like. So first, you will do, the first bond is always the sigma, right? So you'll have the sigma bond in the x direction, okay? Then the second bond is a pi, and the third bond is also a pi, because that is the bonding in the p direction, in the x direction. Now you're going to do bonding in the Y direction, which is a side-to-side overlap over here, right? That's one of the pi bonds. And then you can also have a bond in the Z direction. Going there, down here, and here and here. It looks like a mess and an overlap there. That would give you 3 overlaps. That would give you a triple bond. 1 sigma, 2 pi's. Okay. So this is formaldehyde. The central atom has 3 electron domains, 1, 2, 3. Therefore, it is sp2. Because you add the exponent, it adds up to 3. Okay. The overlap here happens this way. So this one, let me just change my pen. This is the first one's also always a sigma and a sigma, right? And a sigma. So this molecule, formaldehyde, has 3 sigma bonds, and the second bond in a double bond is a pi. So this molecule has 3 sigma bonds and 1 pi bond. Now, how does it look like? The sigma bond between the carbon and the hydrogen looks like this. Here's the hydrogen. Here's the px overlapping with the hydrogen, right? Here's the oxygen over here now. Now you're overlapping in a sigma way over here, right? That's a sigma bond. And then you have a overlap in the pz or py, whatever is being used first, it doesn't matter. But there's a pi overlap here. Okay, that's why you get the double bond. Okay. So in triple bonds, this is acetylene, which looks like this, C1, 2, 3, CH. The drawing looks like this. Here's the C, here's the C. There's the sigma bond. One of those is a sigma. And here's one of the pi bonds. And here's the other pi bond behind in the back. Okay, so in acetylene there is, this is a sigma. Remember, the single bonds are always sigma bonds. So this molecule, acetylene, has 1, 2, 3 sigma bonds and 2 pi bonds.